Hi, my name is William Ting, and this is my brain tumor classification project created in Google Colab and Streamlit. So, firstly, let's go through pre-processing. What we did first is downloaded a Kaggle dataset, which has four different categories: meningioma, pituitary, glioma, and no tumor. And these are types of tumors in the brain. This project can be used for medical professionals, specifically neurologists, who are looking at MRI scans and can help them diagnose certain types of tumors in any MRI scan, right? So in the base project, I had an exception transfer learning model and a CNN model where I created my own uh, CNN with multiple layers. That's more cost effective than the transfer learning model. But here I've also added a ResNet model and a MobileNet model. Now, all of these models have gotten up to 99% accuracy. Of course, certain models are more cost efficient than others, but this is helpful in knowing that certain CNN models will diagnose different MRI scans with different confidences, right? So essentially, the base differences between all these models are kind of the same. So we have we download the model, we train it on certain epochs, and then we try to get it to a really nice validation loss, validation accuracy, blah, 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 blah. We're not just looking for training accuracy, right? Because this is using a very serious topic, and we kind of need these models to be extremely, extremely precise on across all our bases. So let's look at the MobileNet model, for example. Um, we load the base model on certain parameters, compile the model, and then we train the model, right? So with the MobileNet model, something really interesting was that it actually started out with very high accuracy in training, but very low validation accuracy in comparison. Now, this is very high compared to other models, but the way that the MobileNet model trains is that it needs steps per epoch in order to hit um, kind of like those partial steps, right? If we train it based on full epochs, it wouldn't be as effective because it's just constantly overfitting, from what I've seen in testing. So in this case, I train it for 100 epochs. And a lot of the time, somewhere in the arbitrary numbers, let's take this for example, epoch 70, arbitrarily it got a very high training accuracy and precision, a very high recall, and above 99% in validation accuracy and validation precision and recall. However, it's such an arbitrary number, right? Because the very next step, the very next numerous steps actually, it just started going down, but then it would climb back up. So I just chose an arbitrary number 100, and it was still very, very good with the training accuracy. It's just that it seems that according to the charts, the best epoch was likely 88 because of training and validation consistency. So if we're looking at the confusion mixtures, however, it looks like it does very well in training. It's not necessarily overfitted or overtuned. Um, it seems to perform very, very well. So now we have the Streamlit web app. This is essentially this website right here, web page right here, where we can upload files of brain MRI scans, select which model we want to use, and then get the model's prediction for what the brain tumor or no tumor it would be. We also generate a saliency map, and we generate an explanation using one of three LLMs with Google Gemini. There's Gemini Flash, Gemini Flash Turbo, and Gemini Pro. These two models are of the 1.5, Gemini 1.5, and Gemini Flash is Gemini 2.0. So if we just give it a second, it's going to generate an explanation, and then we can also chat with the model. Oh, this just happens sometimes. If we just reselect MobileNet V2, it should be perfectly okay. Just give it a moment. Right. So now it thinks that this file it predicts that this specific image that we've uploaded is a meningioma tumor, and it generates and then inside the Streamlit web app, we generate a saliency map and then we upload that to the model itself. I would love to go through all this, but it's just such a long file. And then it predicts with 100% confidence that it's a meningioma tumor. There's, according to the model, no room for debate here. It is what it is, right? So if we select an LLM, we can generate an explanation as to why the model, most likely why the model thinks the diagnosis is what it is, right? So the model's high confidence in a meningioma diagnosis stems from its focus on the regions along the skull's inner surface, blah, 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 blah. It's explaining why it thinks it's a meningioma tumor. So we can generate a chat as well with the same exact LLM model based on the previous chat, if that makes sense. So what I've done here is created a chat function separate from the generate explanation function that takes in the most previous chat. Let's see if I can find it. I think it's at the very top. Right. So we have the generate explanation, which is this explanation here. And then we have generate chat, which is almost exactly the same prompt, but I've added a little thing here, which is we have already diagnosed the tumor, and the user now wants to discuss with an inputted chat. With the previous chat, and an inputted query, right? So if we can input a query, let's say something like, why is this not a glioma tumor? So because of how Streamlit works, it's just going to regenerate the entire file. So this explanation is going to be redone, but it's essentially going to say the same thing. And then we can look at this chat here. The tumor's location at the skull base with the dural attachment, as highlighted in the saliency map, is classic for a meningioma, not a glioma. Gliomas typically arise within the brain, I can't even say that word, exhibiting different enhancement patterns, blah, 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 blah. So we can see it's very confident and it's explaining exactly why the previous AI model or machine learning model has diagnosed the tumor the way it has. And then we can continue this chat and say something like, I actually disagree with you. I don't see a tumor. So in classic LLM fashion, if you kind of correct them or like say something like, I actually don't think it's this way, blah, 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 a lot of the times LLMs will just blindly agree with you because they're catered most to the user, right? Because technically the way LLMs used to be is that you have an LLM online and then the user is a client. The LLM is trying to adhere to whatever the client wants. This is not the case here because when it comes to medical fields and especially something like this, brain tumor classification, it's very, very crucial that medical professionals and medically trained bots have to be very confident and very they need to be able to defend their answer and then stick with the professional facts, right? So we can look at the chat here. I understand your skepticism, but the MRI, particularly the highlighted areas in light cyan, clearly shows a mass exhibiting features highly suggestive of a meningioma. It is disagreeing with my prompt, right? My prompt is clearly wrong. Factually, it's wrong. Like, even me with my human eyes, I can tell there's a tumor right there, right? But it will, say things like this, give the professional opinion, and then say, however, I respect your perspective and value further investigation, right? Because LLM models are not the end all be all. Just because a machine learning model has diagnosed something, it doesn't mean it's the end all be all. We kind of do need a human professional to verify and to use the data presented by the model, right? It's not a doctor. And the whole point of LLMs is that they're a tool. So yeah, that is my whole project and hope you enjoyed.